Reflectance Spectroscopy of Carbonaceous Meteorites and Insoluble Organic Matter for Interpretation of Spacecraft Data by Kaplan.
Great, thank you. And so it looks like that is working. Very excited to be here, and I would just like to acknowledge a couple of my co-authors down in the bottom left there. And yeah, I'll get to it. So, organic carbon in meteorites. We've kind of touched on this subject a bunch, and we ended the day yesterday with a comment on how maybe we're not all speaking the same language, so I'll just start with some definitions, and the first, 6 slides of this talk will be kind of like making sure everyone's on the same page. And so what I'm really interested in and what I've looked at spectrally is insoluble organic matter. So this is the macromolecular refractive solid. It makes up the majority of the organic matter in meteorites. And it's kerogen-like, though obviously it does not have the same origin. And so what I'm interested in is looking at a bulk meteorite, as evidenced by this big blue box here on the screen, and spectrally being able to understand something about that smaller component that is the organics within that meteorite. And one of the things I'll be talking about a bunch is this hydrogen to carbon ratio of the IOM. Just one measure of the composition of the IOM, and it may be indicative of thermal processing that either the precursor organic material or the meteorite parent body has gone through. So, yeah, we do see evidence of organics in meteorite spectra. So that 3.4 micron region that we've touched on a number of times. And meteorites, we know, contain diverse organic compounds, up to 4 weight % organic carbon. And we know something about how this forms. But it's been suggested previously that this 3.4 micron absorption feature that we're seeing in our reflectance spectra from the laboratory is essentially contamination, that it doesn't reflect, it doesn't reflect the actual organic component of these meteorites. And so I'm going to look farther into that today in this talk. And just to remind everyone about our organic carbon detections in the asteroid belt, these are actually somewhat limited compared to the number of objects that we've looked at from ground-based observations. The asteroid 24 Themis is one detection that we have, and then we have a couple of spacecraft detections, so Ceres, and then maybe not in the asteroid belt, but we have 67P and some other cometary detections of this 3.4 micron feature. And so it's been compared to a number of materials. We expect that it's going to, for the C-type asteroids at least, we expect that the spectral signature will look similar to the spectral signature of our carbonaceous condite meteorites. So that's kind of an assumption going in. So kind of details of reflectance spectroscopy that I like to talk about before going through this, especially because people who don't do reflectance spectroscopy might think that this is quite straightforward, and I think that I would argue that it's not that straightforward. So our spectrum, down in the bottom left here, contains information about the abundance and the composition of minerals, the abundance and the composition of organics, but also something about particle size, albedo, and viewing geometry. And so we need to really disentangle all of this to get qualitative and hopefully quantitative information about the organics in these bulk rocks. And so, again, here's a close-up on this 3.4 micron feature. These are 2 sedimentary rocks that I've shown in the bottom left here. The third spectrum down here is a carbonate, just to keep on everyone's mind that we have this issue that carbonates have overlapping absorptions at 3.4 microns. And so that is something that I don't think has been explored explored very much, and that I think should be thought about a little bit. And so we have the 3.4 micron feature, and so I've just labeled it, but multiple other people have gone through this. We have this aromatic band at shorter wavelengths. It is, I think, due to carbon-hydrogen bonding, so that may be why it is more difficult to see in something where you just have carbon-carbon bonds. That's not really what it's reflecting. And then at longer wavelengths, we have multiple absorptions due to aliphatic carbon-hydrogen. And so what I've done is I have taken spectra of meteorites, and I've taken spectra of IOM, and I've used meteorite and IOM samples where we know something about their composition. So for the meteorites, we know their bulk carbon, we know their bulk hydrogen, a lot of values have been measured for these, and for the IOM, we know their hydrogen and carbon abundances is what I'll concentrate on. So just to show where these values come from, the meteorites, that information comes from the RELAB database, so that's open to anyone. The IOM, I have measured 22 IOM samples in the laboratory, and we've compared these with values that have been measured previously by Connell Alexander. And so just as a final, getting everyone on the same page, here is, I'm going to talk a lot about band depth, which is a really simple measure of absorption strength. And so what I do is, because this 3.4 micron absorption overlaps with some other features, particularly OH and H2O, I take a continuum removal over a smaller amount of, a smaller region, and then measure the absorption strength compared to that continuum removed spectrum. So to start with, the insoluble organic matter. And I see a question down in the side box, which I can answer immediately right now, which is how do we isolate the IOM? And basically we use really strong acids to get rid of everything else, which is amazing to me that the organics are the last thing standing once we've dissolved away the whole rock. And this is an interesting thing to also think about a little bit when we think about like the bulk carbon values. We think actually in that process, maybe we're getting rid of some of our carbon accidentally. So we may have, but that's just something to think about. So anyways, these IOM spectra, again, there are 22 of them. Here I've ordered them by HC ratio because I think it's a interesting way to see how they change spectrally. In general, they are very dark. Usually with albedos less than 3%, and they are typically quite flat, and you see more and more absorption features as you increase your hydrogen to carbon ratio. And so this can also be, we can just concentrate on that 3.4 micron spectral region again, and so here are the same samples that I showed before, and you can see their order again. So one is the strongest, has the strongest absorption. That's the one with the highest hydrogen to carbon ratio, and the bands kind of decreased from there. And so here I think maybe the most important point that I'm going to make today, which is that the absorption strength of this organic region. So here I'm particularly looking at band depth at 3.4 microns on the y-axis, but this works for any of the absorptions in this region. They increase in strength with H to C ratios. And that makes a lot of sense. It makes total physical sense. If you increase H-C ratio, you're increasing typically your amount of aliphatic material. And as you increase your amount of aliphatic material, you're increasing this aliphatic absorption strength. What's really important, though, is understanding at what point do we no longer see these absorptions. And so that we peg at an HC ratio of about 0.3 to 0.4. And so this is really useful when making spacecraft observations. If you don't see an organic signature, does that mean there are no organics there? And the answer is clearly no, they're just outside of your detection range. And I'll talk a lot more about this, our detection space, in a second. A second kind of important point is here are these IOMs, the same plot, but here are kerogens also shown on this plot. And so we have detection limits for the kerogen also, but it's really interesting that they look very different. Their absorption strength related to their composition looks very different. So I think if you're going to go out to another planetary body and model your spectrum with a kerogen, you need to have a good explanation for that, because as far as we know, the kerogen spectra and the IOM look somewhat dissimilar spectrally, and why that is, I don't know. I would love to talk about that for longer, but I'll just leave it at that for now. So, moving on to the carbonaceous cadres. Partly because this is a workshop and also because it's science, I will lay out exactly why you might not trust this data to start with. So, as I mentioned before, sample contamination has been brought up for just any meteorite measured spectrally. Typically, the people measuring them for relab were not interested in the organics, and so did not treat them in the same way an organic chemist might. The spectra were measured at different grain sizes, and so, like I said, particle size can affect band strength. And so all of these are less than 500 microns, and most of them are less than 75 microns, but they're still bound to be scattered because they're measured at different grain sizes. I am comparing spectra that were measured on one sample aliquot to elemental data that was measured on a different sample aliquot. This is the best we can do currently. If anyone would like to give me 50 meteorites to measure spectrally and then dissolve and then measure the IOM spectrally, that would be awesome. I think that would make our life really great. But we know that there is some sample heterogeneity within the meteorites, and it's possible that in measuring two different parts of them, we might have issues. And the relapse spectra are measured in ambient conditions, and so as has been shown previously, we have some adsorbed water in there. You can see if there's enough adsorbed water, what that might do to the strength of these organic bands. And I'll talk about one way in which maybe we can make this particular bit better. But so with all of that in mind, and hopefully otherwise an open mind, I'll go into my data. So here in blue are the IOM spectra, and they're compared to powders and chips of the bulk sample that IOM comes from. So what we see is that the IOM always has stronger absorption, which is kind of to be expected. What I imagine is the IOM is a pure material, and then you dilute it with some amount of meteorites. You're weakening your organic bands. And then the chips have even weaker bands just due to their scattering properties. But you can see that their spectral region retains a fairly similar shape, with the exception of this 3.3 micron shoulder. That's that aromatic region, which seems to completely disappear in the bulk meteorites. And so, yeah, the goal here really is to test whether the absorption strength in the bulk component relates to the organic composition or abundance. And we've kind of done a test study for this, which is now IMPRESS, I believe, with sedimentary rocks and kerogens. So we've shown that this works for a bunch of terrestrial samples, and now we're moving on to meteorites. Just to look at the longer wavelength data, so again, there's this large 3 micron absorption over which the organics are superimposed. but the point I'm trying to make here is in this kind of mid-IR 6 to 7 micron region, we do see absorptions in the IOM that we have attributed to carbon-carbon and carbon-oxygen bonds, which are not seen in any of the bulk meteorites, probably due, again, to overlapping with water and H2O absorptions in that region. So here is a plot where we compare band depth of the spectra to bulk carbon. And for the most part, there's something there. I think you could say that the band depth seems to increase with bulk carbon. The exception is 3 samples, which are all Tagish Lake, which is really interesting. Tagish Lake has an exceptional amount of carbonate. And so this bulk carbon value reflects also the amount of carbonate in the sample. So, again, imperfect measurements. But for the most part, these samples have kind of a background way less than 1 weight % carbonate value, except for Tagish Lake, which has abnormally high carbonate. And you can see that it falls off this line. The band strengths of the organics are weaker than expected based on their carbon content. Based on the IOM spectra, we expect that as HC increases, so will this band depth. And we do kind of see that happening. What's really cool is we see this 0.4 HC cutoff, where below 0.4 we don't really see absorptions, or the absorptions are quite weak. And above it we do see some increasing absorptions, and then you see some that fall off this trend. Sorry, my pointer is not showing, but it doesn't matter. So the yellow points off this trend that fall off that trend, but at high HC values have low bulk carbon. So it's a two-body problem. It's a system. You need to have the right amount of organics in your bulk meteorite, and they need to have the right composition in order for you to see them spectrally. And so here's the plot that really shows this. Here is the parameter space in terms of HC and bulk carbon, where you see absorptions up in that top right corner and where you don't. And just that 1 weight % bulk carbon, it works for this data, but it wasn't pulled out of nowhere. That's based on a bunch of laboratory mixtures. And so those samples with the stars have really weak or below the noise value absorptions or no absorption at all. So, yeah, if you have a detection, so say you're at series and you see an absorption feature, this is really cool because now you can say, well, I think the HC value of these organics is greater than 0.4 and the abundance is greater than 1 weight %. So we have immediately kind of put constraints on any organic detection if we believe that the organics are similar to the meteorite organics. So I talked about that adsorbed water issue because these organic features, that didn't change. Oh, there we go. Because these organic features are superimposed on the bigger water band. And so what I can show is that I can model that water band with Gaussians and then the organic features with the IOM spectrum. And that combined model result allows us to perhaps even better predict the bulk carbon in the samples with a little bit less scatter. And that's probably because you're removing some of the influence of that absorbed water by modeling that 3 micron region. This is really also very cool because by using the strength of one of these Gaussians, the Gaussian closest to 2.7 microns, which is due to hydroxide and probably not, it's not impacted by the absorbed water, we can relate that Gaussian strength directly to the bulk hydrogen in these meteorite samples. And that, I haven't shown it here, but it shows a pretty nice trend similar to this. So basically, you can model these spectra and get out what you think is the bulk carbon and bulk hydrogen. And that really puts an unknown sample within the context of our carbonaceous chondrites really nicely. So a quick overview of what I just talked about. We have these new insoluble organic matter spectra. And we think that there are relationships between carbon and hydrogen and spectral properties for both those spectra and for some bulk meteorite spectra. And I've discussed some methods for estimating organic abundance. So the kind of exciting application, of course, is Ceres. And so this has already been talked about, but this organic detection at Ermitech crater. Here is the strength of this 3.4 micron absorption, and so this map, or the John team's version of this map has already been shown. I recreated it from the data, and our kind of spatial distribution lines up pretty nicely. Our band strings line up nicely, so it's so we're looking at a really nice, strong 3.4 micron absorption feature. And so here at the top, I show the distribution of the strength of this absorption feature. So the strength of the absorption is on the x-axis, and just pixels. So I've looked at one organic rich region and one organic poor region. You can see their variations in 3.4 micron band strength. And so the interesting one is the organic rich region, which spans a pretty big range of band depths. But the most prominent ones, the spectra that have been pulled out by the John team and modeled, tend to have band depths of greater than 0.15, so 15% absorption. And so I've compared that down below on the same band depth x-axis to the carbonaceous meteorites, the IOM, and the Kerogen. So Kerogen, immediately we can kind of just throw out. Okay, we have Kerogens, you know, from very, very, with very high HC values. They have whopping organic bands. They span this whole range easily. The IOM, on the other hand, have a smaller range, and they tend to have band depths less than 0.15. And as I mentioned before, the IOM tend to have stronger absorptions than the bulk meteorites, and so that's kind of shown in the plot also, where besides a few outliers, for the most part, the meteorites have even weaker absorption strength. So Ceres' absorption seems to be very strong compared to our laboratory data. And this may be consistent with the nuclear spectroscopy results that were presented previously, that there may be a lot of organic matter on Ceres, or a lot of carbon on Ceres, at least compared to what we see in our meteorite collection. So I've gone one step further, and I've modeled the organic rich spectrum on Ceres. And so what I've done is I've taken spectral end members, so pure organic, both IOM and Kerogen, just to see how they look different. And then an average spectrum of Ceres. And this is not from the organic rich region, so this is just what Ceres looks like when it's not organic rich. And I've linearly mixed these two components to try and fit the organic rich region. So that's what this looks like. So that green spectrum is the organic rich part of Ceres. And here are fits with a Kerogen and with an IOM. And so what we can do is we can do this for big regions, and we can, sorry, it's not working, okay. And we can understand how much IOM or how much Kerogen is needed to fit that spectrum. And so how much is going to depend on the composition of the end member. These things are not in a vacuum. We don't know the HC at Ceres, so we can measure a range of values. And so for the IOM, we need between 45 and 65% IOM to fit the spectra. For Kerogen, we need 5 to 15% Kerogen. And this makes sense, as I showed before, the Kerogen have much stronger bands than the IOM. But this number is really high. And so, yeah, I think it brings up a lot of interesting questions about, in terms of implications for Ceres. And we've already discussed, you know, is this an impactor? Is this coming from the interior? And I think these results at least hopefully start to put constraints on what the organic abundances may be that we're going to have to fit. So Ceres exhibits a very strong 3.4 micron region, and we need a lot of IOM to fit that. But the kind of important caveat here, and the important thing to keep in mind, I think, in general, is that abundances that we derive from spectral modeling are going to depend on the composition of the organic spectral end member. And so here I've presented a range of organic spectral end members, the IOM, with a range of compositions that would be really useful for this problem and have been really useful. And I think that's something important to keep in mind. And so here are just the final conclusions. The 3.4 micron absorption, the aliphatic absorption reflects both abundance and composition of the organic series results. And so for me, the outstanding questions here are, what is the influence of carbonates in the 3.4 micron region? We know there are carbonates in the meteorites and at Ceres, and how is that influencing the strength of this 3.4 micron absorption? How is space weathering influencing these absorptions? Is the reason that we don't see organics elsewhere on the surface of Ceres besides near Earth a matter of them being space weathered to HC values or abundances below which we can spectrally detect them? And then what's the distribution of organics in the asteroid belt? Are we missing things with our spectral catalog? So yeah. Question.
Yeah, who has questions?
I have a question.
Yes. Have you measured the carbon contents in each of your IOM and kerogen samples, and can you correlate this to band depth? Can you also correlate the abundance of the aliphatic fraction in each sample with the band depth? So we don't have the abundance of the aliphatic fraction. We have not measured that for our samples. We do have carbon content for the IOM and the kerogens. And this does correlate to band depth somewhat, but you really need to account for that hydrogen in there. You could have as much carbon as you want, but if there's no hydrogen bonded to it, you don't see absorption here. So it's really a function, I think, less of the carbon content, and actually I think of it more as the organic hydrogen content, which of course we don't really measure, so it's, you know, that's not something, as far as I know, that I would go out and measure on a kerogen, but that is kind of, that to me is the most direct thing that that band reflects.
I have a question.
Yeah.
So, in regards to this decomulving the carbonates,
Yeah.
which is obviously hard, but there's, so you said there's another band for carbonates at 3.4.
Yeah.
And Simone showed that there's a spatial correlation between these organic rich regions and the carbonate rich regions. So, do you anticipate when you account for that, lowering this 45 to 65% IOM abundance down considerably?
So I think that's a possibility, and I think it's something Simone and I can talk about because I've done the same thing, and I don't see an elevated carbonate value compared to background in this region.
Can you actually separate and say, like, hey, this is the band for carbonates and this is the band for...
So there's another carbonate band at 4 microns, which is what I've used. So seeing how the strength of that varies, I assume varies directly with the amount of carbonate. But it's not totally straightforward in the 3.4 micron region because, especially in the meteorites, you can see a 4 micron band and not see a 3.4 due to carbonate. So it's, yeah, I don't think it's straightforward, and I think we should talk about the carbonates some more because it doesn't totally match with what I'm seeing, but I think that would explain something.
Yeah, I also have a question related to a statement in this slide. It says, in general, IOM spectra facilitates spectral modeling for meteorites and asteroids. Can you elaborate this a little bit more? Perhaps, are you saying that the IOM is a better fit to what we see on Ceres, that, for instance, Carbonaceous that's been used previously?
Yeah, so that's exactly my argument. My argument is that we are talking about extraterrestrial organics, and we need to use relevant reflectance spectra. And I showed how the kerogens are quite different than, and carite also will be similar to kerogen. they are different than the IOM, so unless you want to argue that we think Sirius is more Kerogen-like than IOM-like, and you can make that argument for a number of reasons based on the type of organics, the chain length of the aliphatics, perhaps. But I think the first step to me would always be to use the IOM, the thing that we think of as being most relevant to these bodies, before then saying, oh, but it might be Kerite-like.
Right. So I guess there is a very important consequence. If this is correct, if the IOM is really what's observed on Sirius,
yes,
then the consequence is that there is a huge amount.
Yes, exactly.
Which it's intriguing, also a little bit disturbing, because I don't know how you would get 50% like that. So
yeah.
I think that it's a very intriguing problem.
Yes, I think so to me that is totally the outcome of this series work, and that's in review right now. And if you're one of my reviewers, maybe you should turn it in. Yeah, so I think that is, to me, the most intriguing outcome, is if you use IOM, you get a lot of organics. So maybe within the range of what we see for comets. So I think 67P has like 50 weight percent organic. Why this one region of Sirius is comet-like that? I don't think you don't get that by impact, obviously. That much doesn't survive impact.
Well, it is not comet-like, no matter what, because there are carbonates and lots of other things, so yeah.
Sure.
This is Dale. I have a question here. In one of your summary slides along the way, you made a point of the absence of aromatic CH stretch, yet in a slide before that, where you showed superimposed reflectance spectra of 7 or 8 different meteorites, one of them at least did in fact show something at 3.28, and I would suggest that maybe going back to look at that a little more carefully, you might not want to eliminate the possibility that at least some of these, this one, I think that was it. Some of these may show a weak feature at 3.28, and I'm fixated on that. Sorry?
These are the pure organic. And so my argument is that when you move to the meteorite spectra, the bulk meteorites, you don't see the 3.28. But in here, I would say you definitely see the 3.28, because these are pure organic spectra.
Okay, well, that's fine with me. Any way you want to make the 3.28 is of interest, I think, in the context of what I was talking about earlier. Tagish is not shown in this particular diagram, but as I noted, a spectrum that I got from Connell Alexander some years ago did show something at 3.28 in Tagish. So even if it only shows up rarely, it's of interest. I think in the context of Phoebe and the other things that we find in the Saturn system. On the other hand, what you've done is present really a comprehensive look at this part of the spectrum in these meteorites, and I think this will be a valuable data set for a long time to come. Nicely done.
Thank you. And yeah, so part of that comprehensive data set is 3.28 measurements for all the meteorites, so I can easily go back and look and see where we see it and where we don't. Yeah. It is rare, but I think we do see it in a few of them, for sure.
Okay, good. Glad to hear that. Thank you.
And I'd like to say something too. Hannah, that was just a fabulous talk, and I'm really excited by your work. And the strength of that 3.38 micron feature there that both you and I were noting yesterday, I think is telling us something really important in these both the IOM and the interstellar medium. And laboratory experiments where you create these 3.4 micron bands, unless you start out with a lot of methane, they just do not lead to that strength in that band. So anyhow, I want to talk to you more about perhaps modeling some of our data together.
Yeah, absolutely. And that is one of the major differences with the Kerogen, too, is the Kerogens don't have that strong 3.38 band. I think because of the length of the aliphatic chains, they don't have the amount of methane groups. Yeah, so that's really cool.
Great.
that another thing?
Oh, that's,
We've done that.
we've done
Okay.
that. Yeah.
Want to move on then?